Hello, and welcome to the Chapter 2.2 lecture on separable differential equations. So this is exciting because in this chapter, we'll actually learn how to solve differential equations from scratch, as opposed to what we've been doing, which was all necessary work. But so far, we have just been learning what differential equations are, how they behave, how to model real-life situations with differential equations, and how to solve initial value problems, which we'll be needing to do anyway. But now, we can solve differential equations from scratch. First, let's talk about the simplest kind of differential equation. Back in Calculus 1, you were actually technically solving really simple differential equations. A differential equation of the form dy dx is just f of x. So, for example, dy dx is x squared. To solve this, we just integrate both sides, dx. Integral of dy dx is y. That's the fundamental theorem of calculus. And integral of x squared dx is 1/3 x cubed. And don't forget the plus c. So that's not interesting. We're interested in actual differential equations. And the first type of actual differential equation that we'll learn, and which this section is dedicated to, is separable differential equations. So a first-order differential equation of the form dy dx equals g of x times h of y is called separable. Separable in the sense that we can separate the x part and the y part into two distinct parts, of which we're taking the product. So, for example, dy dx is x squared sine of y is separable because this is a function of x only, while this is a function of y only. So that's a yes. And sometimes differential equations may be in a different form, presented that way at least, where it's not immediately obvious if they're separable. And to find if they're separable, we need to rearrange them, get them in standard form, isolate the dy dx, and see if we can separate like that. So in this case, first y prime, that's the same as dy dx. We want to isolate that dy dx, get into standard form. So we have that. And now dividing both sides by x squared, we have 2 over x times y, and that is separate. That's a function of x only times a function of y only. And some non-examples, not every differential equation is separable. So for example, dy dx is sine of xy. You might think, oh, well, that's a function of x only and y only. No, I mean, inside, yes, but the definition of a separable differential equation is that the entire right-hand side must be g of x times h of y. And this is very much not equal to something like sine of x times sine of y. It can't be expressed as a product of a function of x only and a function of y only. So we can't separate that as dy dx is f of x times g of y. Is this guy separable? So it looks like it's a single function of x and y. So it's not really separate in this form, but using exponential laws, that's the same as e to the x times e to the y. So that is a function of x only times a function of y only. That's a yes. And I should clarify, if we can rearrange it into a separable or separate form, then the original is called separable. And for a differential equation to be separable, it needs to be a product of two functions, one of which is of x only, one of which is y. So this looks separated. It's separated by a plus, but that is not separable because for it to be a separable equation, it must be a product, f of x times g of y, not a sum. Okay, we've talked enough about what separable differential equations are. Why do we care? Well, it turns out that separable differential equations are really quite easy to solve in the following way. What we do is we can separate them such that the y parts are on one side the x parts are on the other. So this differential equation, all I did here was I multiplied both sides by dx, got it there, and divided both sides by y. Dividing both sides by y made a 1 over y on that side. So now these are y's only, while these guys are x's only. Now this is a relationship, an equality between infinitesimals. And we can add two equations together. So like we could have x plus y is 2, 2x plus 3y is 5. We could add those together, and we would have 3x plus 4y is 7. And we can do the same thing with different equalities of infinitesimals. And what this is saying is that no matter what x and y are, we have this equality. So what we can do is consider an infinite number of equations of this form for different x's and y's at different points. And we have an infinite array of equations of infinitesimals, and we can add all of those together. So in other words, we're adding together infinitely many infinitesimals on both sides through adding the equations together like this. But what's an infinite sum of infinitesimals? That's right, it's an integral. So we can integrate both sides with respect to their respective variables. Integral of 1 over y is ln y, and integral of x is 1/2 x squared. Don't forget the plus c. That plus c will become that arbitrary constant that we did a lot of practice for solving for in initial value problems. And by the way, technically there would also be a plus c on the left-hand side. Let me show you what happens. So it's like plus c1 there equals 1/2 x squared plus another arbitrary constant. We can move that to the other side like that. And a difference of two arbitrary constants. So imagine as c1 and c2 range across all real numbers, then their difference can also be any real number. So we can just call this another arbitrary constant. So that's what that is. And that's the solution. That's all there is to it. You separate, integrate both sides, and you have your solution. That is an implicit solution, but an implicit solution is a solution. Often, though, we'll want explicit solutions. So getting an explicit solution is just a matter of solving for y. So how can we solve for y in this equation? Well, we want to get rid of the natural log. Opposite of natural log is exponentiation. So we got this. To get an explicit solution, we can take e to the power of both sides. E to the ln y is y. And okay, this is okay, but it can be simplified. We have an e to the power of something plus something. Exponent laws tell us that's e to the 1/2 x squared times e to the c. And we'll be doing this a lot in the same way that we renamed a difference of arbitrary constants as another arbitrary constant. As c ranges across all real numbers, e to the c can be any positive number. Technically, as c ranges across all numbers, including complex, it could also be negative. Don't worry about it. Don't worry about that part. As c ranges across all real numbers, e to the c can be any positive number. So we'll just rename this as another arbitrary constant. We'll rename that to be c. What we're doing is simplifying. It's a bit of an abuse of notation. It's not the same arbitrary constant. The point is it's an arbitrary constant. So we wind up with y is c times e to the 1/2 x squared. Okay, so this guy that we initially got, that's an implicit solution, while this guy is our explicit solution. And this will be common in solving differential equations. We'll often get an implicit solution when we solve, and then we'll need to do some algebraic rearrangement, being aware of how we can manipulate the arbitrary constants, renaming them to simplify, to get an explicit solution. And we can always check our work by plugging back in, making sure it checks out. So the derivative of this is x times e to the 1/2 x squared times c, and that is indeed x times e to the 1/2 x squared times c. So it does check out if you plug it back in. Okay, now I want to take this moment to point out a common error. You need to fully separate. So if we were to consider something like dy dx is xy, like in the previous example, and then we thought, okay, that means that dy is xy dx. So far, that's true. And then we decided to integrate both sides right off the bat. And remember, there's like a 1 here. Whenever you see just the integral of dy, it's the integral of 1. So this guy would be y. Okay, going from this step to this step is a giant no. That's a no because they are not separated. You might think, okay, well, at this point, that left-hand side, integral of 1 dy is y, and integral of xy dx, that's like y is a constant, so you might think, okay, that's 1/2 x squared y. Again, that's no for the same reason. This step is fundamentally invalid. And the reason it's invalid is that treating y as like a constant here, as we did when we integrated, it's not true that y is a constant relative to x. Y is a function of x, it varies with x. So you can't just treat y as a constant and integrate with respect to x. That is why you need to fully separate, like we did. And as you can see, we got a completely different answer. This is a wrong answer. If you plug it in, it won't work. So make sure that when you're solving these, you completely separate, like we did over here, writing it as 1 over y dy is x dx. That was completely separated with y's only on the left-hand side, x's only on the right-hand side. This had both x's and y's on the right-hand side. Okay, in this initial slide, what's going on here, that's what I already said about how it's adding together an infinite number of infinitesimals, and that's why we can integrate both sides if they're separated. Otherwise, it's not legit for that reason. So on the very first slide of the very first lecture, we had a look at this equation. And we guessed a solution. We thought, okay, what function is its own derivative? And we guessed e to the x. That's true. That's one of the solutions. Now we can actually prove it, find all solutions, and prove that c times e to the x is the entire family of solutions and nothing else. And this also serves as a lesson in that whenever you see a y prime, that's dy dx, and that's necessary to separate. So this is dy dx is y. We want to separate, multiply both sides by dx. Remember, you cannot integrate yet. This is not separated yet. We need to get y's exclusively on one side, x's exclusively on the other. So divide both sides by y, and we have this. Now we have y's only there, and x's only there. So now we can integrate. So integral of 1 over y dy is integral of dx. Remember, whenever you see integral of dx, there's a secret 1 right there. Integral of 1 times dx. And integral of 1 is x. Don't forget the plus c. Integral of 1 over y is ln y. So in Calc 2, if your calculus teacher ever berated you for not writing the plus c, well, now you can really see why we always need it. It gets the full family of solutions. And without that, we can't solve initial value problems. Okay, so we get this. That's fine as an implicit solution. But if we wanted an explicit solution, we need to solve for y. Undoing the natural log, we take e to the power of both sides. And remember our usual trick, e to the c, if c varies, so does e to the c as just another arbitrary constant. So we'll rename that to c. It's just another arbitrary constant. So y is e to the x times c, better known as y is c times e to the x. So that's our explicit solution. And that's the full family of solutions that satisfies y prime equals y. Okay, so you try your hand. Go ahead and find the general solution to this differential equation. Pause the video. All right, so dy dx, always write the y prime as dy dx, is xy squared. We separate 1 over y squared dy is x dx. fully separated. Can't emphasize that enough. You have to fully separate before you integrate both sides. Integral of 1 over y squared is negative 1 over y. Remember, 1 over y squared, it means y to the negative 2. And the integral of y to the negative 2, we just increase the exponent by 1 and divide by it. So that's 1 over negative 1 times y to the negative 1, which is negative 1 over y. Is 1/2 x squared plus c. Okay, and that's our implicit solution. Perfectly fine, although we typically want explicit. Okay, and to get an explicit, let's take the reciprocal of both sides. So now we have negative y is 1 over 1/2 x squared plus c. That 1/2 down there is ugly. Let's multiply this by 2 over 2 and multiply both sides by negative 1 while we're at it. Okay, so that's multiplying both sides by negative 1 is now negative. And to get rid of that 1/2, let's multiply by 2 over 2. So we have negative 2 over x squared plus 2c. And now a lot of things can get absorbed in c. If c varies to be any real number, so does 2c. So we'll just rename this to c because it's just another arbitrary constant. So we get our explicit solution. And we have solved the differential equation. You might even recognize this. We did initial value problems with this before, and we verified that it's a solution to this in a previous lecture. So if we were given this differential equation plus an initial value, the first thing we would do is do all of this, and then we would solve for c given the initial value in exactly the same way that we did in previous lectures. But that's the general solution. Oh, and speaking of which, here it is. Let's solve the initial value problem. Y prime equals xy squared with initial value y of 0 equals 2. So step 1 for doing these is to find the general solution to the differential equation, and that's what we already did. We found that y prime equals xy squared has general solution y is negative 2 over x squared plus c. And then step 2 is to solve for that arbitrary constant given the initial value. Okay, we learned how to do this, but let's do a refresher by working through it. Okay, so we know that the general solution is this. We know the y of 0 is 2. So y of 0, that's negative 2 over 0 squared plus c, must be equal to 2. I mean, that's x, we plug it in for x, and it must have output 2. So negative 2 over c is 2, and thus c is negative 1. So the solution to the initial value problem, IVP initial value problem, is y is negative 2 over x squared minus 1. Since that was c. And I'm always one for making things prettier. We can multiply this by negative 1 over negative 1, and this is 2 over 1 minus x squared. All right, congrats. So we now know how to solve initial value problems from scratch, at least if the differential equation is separable. Now I must give a warning. When you are doing dividing in separating variables, you can lose solutions because you could be dividing by 0, which means that you're really saying y is not 0. So for example, here, this is dy dx equals y squared. So we might think, okay, therefore 1 over y squared dy is dx. The nuance is that going from here to here, that is assuming that y is not equal to 0. Let's get back to that in a moment. Now we can integrate both sides, assuming y is not 0. We have our secret 1 there. And this is negative 1 over y is x plus c. So y is negative 1 over x plus c. Okay, or y is 0. And you can verify that y equals 0 is a solution, but none of these guys is 0. You can think of it as it becomes 0 as the arbitrary constant becomes arbitrarily large. Then it's like 1 over infinity is like 0, but it's technically not included in this. So be warned about losing solutions. It's something that one never really has to worry about because the lost solutions will typically just be 0, and we're not interested in a solution of 0 because in practice we'll be solving these for some kind of changing state system where it's not just 0. But worth noting. And technically, even in this example, I didn't want to complicate it then, but we got that y was -2 over x squared plus c. But when we did that, we divided both sides by y squared, just like we did here, and implicitly lost the 0 solution because we were assuming it wasn't 0. So, or y is 0. That's like a technicality, but in mathematics, we want to be technically correct. Okay, so you did your hand at solving one separable differential equation. Try your hand at another. This time it's an initial value problem. And as you can see, this one is straight from the homework. You'll just have different numbers. Okay, take a minute. All right, so we have dy dt is 1 minus 2y. And separating, we have 1 over 1 minus 2y dy is dt. Separating, we have this. Dividing both sides by 1 minus 2y, multiplying both sides by dt. So now we have a function of y only equal to a function of t's only. And that's what we need always before we can integrate both sides. Don't make that mistake. Must be fully separated. Okay, so we have this. Integral of dt is integral of 1 times dt. So that right-hand side, integral of 1 is t. Don't forget the plus c. And the left-hand side, we have to undo the chain rule here. We can do a u substitution if we want. The way I think about it is, okay, if I regard this whole thing as just a single variable, like, call this u, integral of 1 over u would be the natural log of that. So we have the natural log of 1 minus 2y. And now I think, okay, but when I differentiate this, then it will pull out that minus 2 because derivative of -2y is minus 2. So I need to compensate for that by dividing by that -2. At least that's what goes through my head to do these kinds of integrals quickly. I kind of do a rough, sketchy integral, and I imagine differentiating it and think of, okay, what do I need to get it to differentiate correctly? But if you just prefer u substitution, you can always do that. Regardless, this is what we get. Okay, and implicitly, it wants an explicit solution. That's typically the case. So let's solve for y. First, let's isolate the natural log, and we have this. You might think, wait, did he just make an error? Because isn't that a -2c? Well, remember, -2c, we can just rename that to bc. As c varies across all real numbers, so does -2c. Now we can take e to the power of both sides. Okay, and that's the same as e to the -2t times e to the c. And this guy, again, we'll just rename it to c. As c varies across all real numbers, so does e to the c. And we have 1 minus 2y is c times e to the -2t. And y is 1/2 minus 1/2 c e to the -2t. And now let's do this yet again. As c varies across all real numbers, so does -1/2 c. So we'll just call that c, another arbitrary constant. And this is our explicit solution. And we can always plug it in, verify, and it does work. And now solving the initial value problem, we plug in y of 0, that's 1/2 plus c e to the -2 times 0 must be 5/2. E to the 0 is 1, so we get that. And thus c is 2. So our solution to this initial value problem is 1/2 plus 2 e to the -2t. All right, that just about concludes this lecture. We now know how to solve separable differential equations and initial value problems associated with them. There are just a couple more little pieces of terminology. A singular point of a first-order differential equation is a point at which one of its terms is undefined in normal form. dy dx is this, just solving for dy dx. And as you can see, we're dividing by 0 when x is equal to 0. So there is no solution when x is 0. And that's because this guy is the slope, dy dx. So what this is saying is there's like an infinite slope when x is 0, so no possible solution can pass through that. So x equals 0 is a singular point. So when it says think about the implications of any singular points, this is what it's talking about. So no solution can be defined there. So the largest interval over which it could be defined, if the solution is defined at all other points, would be 0 to infinity, or negative infinity to 0, because it can't be defined at x equals 0. And yeah, we could work through this, find the general solution to this. It turns out to be separable. And I want to point out that if we were to solve this differential equation, one can do the manipulations we've kind of been doing and separate the variables and integrate and solve. Then we turn out to get that y is cx minus x cosine x. To be clear, that's skipping steps, but it's doing exactly what we've done this whole lecture. And looking at this, it doesn't look like it's undefined anywhere. However, the singular point told us that we can never pass through x equals 0. So because this is not undefined anywhere else, but we can't pass through x equals 0 due to the singular point, that is still the largest interval of definition, or negative infinity to 0. Okay, that does conclude chapter 2.2. Have a great one.